A little bit. Yeah. What we are doing here? The topic D.3, linear recurrence relations. What is the goal we are doing here? Yeah. So here we are at the step like this, because we verified the Fibonacci formulas, Fibonacci formula, yeah. And but one thing not quite there, that is, how do you know that formula, right? How can you discover, how do you discover that formula, right? Yeah, because nobody can guess a formula like that, unusual, using golden ratio. Nobody can connect Fibonacci numbers to golden ratio directly, right? Yeah. So here we need to do this, derive the Fibonacci formula. Fibonacci formula. How do you derive Fibonacci formula? By solving linear recurrence relation. So that's what I am doing in D.3. Okay. All right. So let's look at our question description. Yeah. So we need to solve the recurrence relation. The original recurrence relation. At the end, the formula should look like this. Yeah. But here it's not a verification. Yeah. So we need to find it explicitly. All right. Yeah. Before that, let us look at the relation type, recurrence relation type. Now, what kind of problem it is? All right. Yeah. So it is called, look at this long name, second order linear homogeneous recurrence relation with constant coefficients. That's the full name of this equation type, this relation type. How long? Yeah, that long. In order to describe it completely, we have this long name. Let me explain one by one. Second order, not first order, second order. When you look at the right-hand side of this recurrence relation, there are two terms, 1, 2, related to the recursive function. Two terms about recursive functions. Yeah. That means second order. If there is only one term, then that's the first order. Two terms, second order, and so on. All right. So that's first. Second, linear. Linear, each term is a linear term because there is no square term. There is no non-linear term. All right. So linear, you know the linear term, right? Ax plus b, a could be constant, b could be constant. Then the variable part, only the variable itself, linear. That's the linear expression. Yeah. Here, the right-hand side, we have the linear expression. So that's why we call it linear. Yeah. Third one, homogeneous. So what's the homogeneous? Homogeneous, that means the constant C equals 0. Okay. Yeah, because here, other than these two terms, sometimes people can plus a constant c. Here, our constant c happens to be 0. So when a linear system with constant part 0, people call it homogeneous equations. So here we use this homogeneous to describe constant 0 part. All right, that recurrence relation with constant coefficient. Yeah, coefficient here 1, coefficient for the first f term 1, second f term also 1. So that's the linear, that's the constant coefficients. All right, so you can see that's the reason we have a long name for this question type. Now let us, go to the analysis part and try to find a solution. All right, so based on the general equation type, here we write, so this is the general expression for the question type. AK, little ak equals capital A times little a sub k minus 1 plus b times little a sub k minus 2 with b not equal to 0. All right, but for our Fibonacci numbers question, we have a equals b equals 1. So that is a special, simple, second order linear homogeneous recurrence relation. Yeah, as simple as this one. Little ak equals little a sub k minus 1 plus little a sub k minus 2. Okay, all right. Now let us try to discover the solution, but you have to do the logical reasoning along some reasonable path, because it's very hard to jump quickly to the destination, right? You have to do a lot of work. So let's start. Look at the relatively simple view of it. Take a special view. Now, let us consider AK sequence, because with a given recurrence relation, we can generate a sequence, right? AK sequence. Here, let us study the AK sequence. What kind of structure this sequence should have? All right, so here we need to guess its structure. What structure should we use to describe that AK sequence? Yeah, so this part, if you can find the right structure, it may not be that easy. Yeah, so here, can we think of this special structure T to the kth power, T to the kth power structure? You may ask why? Yeah, because if you cannot provide some reasonable explanation, how can you guess the structure like this, right? Here, let me provide some rationale behind it. Yeah. All right. Let us consider first order linear homogeneous recurrence relation. How about that? Yeah. Second order, relatively hard. Can we talk about the first order linear homogeneous equation? All right. Yeah. Look at this. Yeah. Let me write AK equals alpha times A sub K minus 1. How about that? That's simple, right? Alpha some constant. Okay? Yeah. If you try out solving this simple case, you can find the solution easily, right? Think about that. Okay? Yeah. Because if you do iteration to the next round, you will get alpha squared A sub K minus 2 and so on. Okay? Yeah. At the end, you may get alpha to the K. How about that? Yeah. How about that? Assume A0 equals 1. Assume A0 equals 1. Okay? Yeah. At the end, AK equals alpha to the kth power. Look at that. What is this structure? Power function, right? Monomial. It is a monomial, right? Power function monomial. Okay? Yeah. All right. Now we guess the structure based on the special case, the first order linear homogeneous recurrence relation. There is some base, right? Not baseless guess, right? Yeah, something we can base on. That is the first order case. Yeah. But it may not work. You can make this guess, but it may not work, right? Let us try it. Yeah. Let us use this structure to try what can we get with this brave guess. Yeah. All right. Yeah. So let's do the work. Yeah. All right. We know it is a geometric sequence. Yes. Now let us try to find that t. What is that t? Right? What is that t? We have freedom to set value for that t unknown part. The freedom, we have that freedom. That freedom is useful here. Yeah. All right, so ignore the initial condition first. Yes. When we try to find a solution, let us delay the initial condition part. Yeah. Only work on the main part. Yeah. All right. Now we want to find a solution using this structure, okay, power function structure or geometric sequence structure. All right. Let us plug in into our main recurrence relation. That becomes t to the k equals t to the k minus 1 plus t to the k minus 2. Yeah, each term, it's a monomial, okay? Yeah, it's a polynomial equation. That is much easier than our original equation, right? Yeah, so let's try to solve. Let us do simplification, both sides. Yeah, so we will get t squared equals t plus 1. We're familiar with this equation, right? This quadratic equation. Remember, we derived the golden ratio from this equation. Now, you can see in this way, we connect to the golden ratio. We can find a t value here, similar to we find the golden ratio expression. Okay, yeah. By solving this quadratic equation. We have a quadratic formula, so we can plug in, solving this quadratic equation, we get two solutions. T1 equals 1 plus root 5 over 2, and T2 equals 1 minus root 5 over 2. Two possible solutions. Two solutions for the quadratic equation. But this time, our T is not necessarily golden ratio, right? Because we do not assume that T is golden ratio. We do not have any assumption on that T, right? Remember, in the golden ratio case, when we find two possible solutions, we drop the negative one because we know the golden ratio cannot be negative. But here, our T is not necessarily the golden ratio, and we do not have any geometric meaning for T. That means negative solution is allowed, right? Negative solution is allowed. There is no reason to drop the negative solution. So T2 is qualified as a special case for the solution. So we should keep both solutions, T1, T2. Yeah. All right, now at this point, we get some valuable partial result. Partial result, very valuable. We need to make use of this valuable partial result and go to the next step. Okay, all right. Here we have two special solutions for this quadratic equation. Yeah. T1, T2. All right. Now, that means if we plug in T1 or T2 into the original recurrence relation formula, we have first expression by plugging T1. Second, by plugging T2. We have these two equalities, right? These two equalities, both correct, right? Yeah. They are not integers, don't worry. We do not require T as integers, right? T can be any real number. Yeah, we do not require they are integer solutions. Yeah. So these two equalities are fine. Yeah. All right. Then the question, right? After we get these two equalities, the next question we need to think about: initial condition. Initial condition. Make our final solution satisfy initial condition. These two solutions do not satisfy the initial condition. So we cannot use these two possible solutions as our final solutions. We cannot. Okay? So we need to do some critical work to get final solution. Critical work. How to bridge the gap? There is a big gap. There is a big gap between the current intermediate solution and our destination final solution. That big gap, we need to find some special technique to bridge them. Bridge it. All right. Yeah. Let's look at that part. Question: how to use two special solutions without the initial condition to get a new solution with the initial condition? This is our new question. Okay. We can use some special way. Yeah. So our current information, we can use these two special solutions. We can manipulate these two special solutions. Manipulate for what? For a new solution expression. Manipulate two old solutions to get a new solution. And how do you know your new solution is correct? We use the initial condition to tell us if the new solution is correct. Okay, yeah. Here you can see initial condition is useful here. All right. Question, is there a special way to combine two solutions? Yes. How do you combine two solutions, right? Do you have some special, reasonable way to combine those two old solutions? That question is important. In which way you feel is a reasonable, natural way to combine two old solutions? That's our current question. Yeah. All right. Now let us look at a special mathematical concept we can use to combine those two solutions. Yeah. So what's that? All right. It is called a linear combination of two variables, x and y. In math, there is a concept called a linear combination. How do we combine two variables for a new expression? There is one simple concept. It is called linear combination of two variables. Let us do it. Linear combination. Okay. So what is the linear combination? You use this form. Ax plus by. A is a constant. B another constant. Two constant we can use to form linear combination of two variables to get a new expression. Here, let us borrow this idea to combine our old solution, two old solutions for a new solution expression. How about that? This idea. Okay, let us do linear combination. All right, yeah. All right, yeah, two constant. What two constants should we use? We will determine later. At this point, let us use unknown parameters, A and B. We will determine these two parameters later. Okay, yeah. At this point, they are unknown. All right. Question, how to take advantage of this linearity property? Here, we talk about linearity property. What's the linearity property? Remember, our original recurrence relation is a linear recurrence relation. Linear is useful here. Linear means that equation has the linearity property. So here we need to take advantage of that linearity property. How to take advantage? Yeah, so let me do it, show you how to take advantage of this property. Any linear combination of two solutions is also a solution. This is the new property derived from that linearity property. Yeah, look at this. All right, let us use the linear combination of two old solutions. First one, A parameter times the first solution plus B parameter times the second solution. Here the question, can you see this new expression gives us a new solution for any capital A and a capital B? Although we do not know what are the values for A and B, but don't worry, for any capital A, capital B, this form is always a solution. Can you see that? Can you see that? Yeah. So in order to see that, let me go back to the previous slide a little bit. Yeah, let me, backtrack to the, oh, yeah, here. All right, so here. Now we are here. Okay. The first equation, this equation, can we multiply A both sides? A. Second equality, let's multiply capital B both sides. B. Then let us add up two equalities, both sides together. Can you see we get a new solution? A, that big parenthesis to the nth, plus B, that big parenthesis to the nth, equals right-hand side similar structure. Is that format follows exactly our original recurrence relation? Can you see that? This trick works because of the linearity property. If we do not have that linearity property, we cannot do in this way, or this way won't work. Here, we take advantage of that linearity property, so this combination way works. All right, let me move to the next slide. The same point. Yeah, here. All right. Now, this general form, yeah, we can, pretty general, because for any capital A, any capital B, this form is a valid solution. Now the question is how to determine capital A, capital B. Okay. Initial condition. Initial condition. All right. Okay, that's easy. Yeah. Let us bring in initial values here and try to find capital A, capital B. Yeah. Let's plug in when A equals 0. A0 equals this expression, and we can simplify it. A plus B equals 0. That means B equals negative A. A1, when n equals 1, little a sub 1 equals this expression, and we can replace B by minus A. That is E0, that is 1. So we can find, after simplification, we find A times root 5 equals 1. That means A equals 1 over root 5. After that, B equals negative 1 over root 5. A, B, two parameters are discovered. So the last step, we can write an explicit formula for our solution completely. That is, here we can, because we define golden ratio for this expression, yeah, we can use golden ratio here, yeah. And the second part, negative 1 over the golden ratio. So at the final form for the solution, that is our original, the form we are familiar with, Fibonacci formula. Look at that. That's the whole development procedure. Whole development procedure. All right. Yeah. Please try your best to understand this procedure, the story behind it. Yeah. I went through a long story. Yeah. So try to understand yourself, and because I like you to be able to solve equations like this. Yeah. So I may give you some questions solving this kind of recurrence relation for yourself. Yeah. As I know, you learned how to solve this kind of problems in your discrete math. Yeah. Math 3000, discrete math. Yeah. And at that time, you have some standard way to solve. Yeah. I saw some students using their, old way to solve. Yeah. Yeah. How do you solve? It's not important. The only thing important at the end, you find the right solution. Yeah. That will be important. Okay. All right. So we complete this part D of module 3 and the whole module 3 completed. Yeah. All right. Next, let us move to module 4.